Hey guys, so what I want to do for today is just take a quick look at those two pages I wanted you to read through yesterday. Make sure that you're understanding what I'm writing there. Go through an example of how to write the Fourier series then using these formulas for a square wave function. Okay, the first page here, what we're looking at here, basically extends the idea of vector spaces to functions, right? We have seen that functions behave with linearity. Um, f of t plus g of t equals f plus g of t. You can draw it out, and then scaling works as well. Um, so because of that, you can sort of think of them as vectors in a space. Um, for your information, like if you want to look more about this, like idea of this infinite space, by the way, it's called, this is just the Wikipedia. I just literally Googled Hilbert space, and this is the first thing that popped up. It's probably more than adequate. But if you look at this quickly, like if you want to see more about it, it extends the ideas of a Hilbert space, basically takes into account an infinite vector space. So it extends a lot of the ideas from linear algebra to an infinite dimensional space, which is what we have here. Because if we're saying that we can write out any periodic function as an infinite series of sines and cosines, then the vectors in this space would be infinite in their dimension, essentially. But we have two different ways of looking at the fact that sine and cosine are orthogonal. Three, if you count like the fact that they're in the name cosine. Cosine is the CO is the complement of sine, meaning it's the same thing but 90 degrees later. Just like cosecant and secant are the same values 90 degrees apart, tangent and cotangent as well. But you can see it through calculus here clearly that basically they have this is like a dot product for us, right? We're multiplying, this is the integral of the product of sine and cosine, and then looking at that in, so it's an infinite, it's an infinite, if you, all the values from 0 to 2 pi, still infinite, right? And so if you look at that, you've got an orthogonal basis of basically functions or vectors that will help you to write this. So what we're writing out here, like this infinite series, like I had you watch that quick Khan Academy video late last week. This is these coefficients that we're looking for here in this series. Now that can understand this a little bit better, that's the linear combination. That's the scaled versions of sine and cos. Like it's the recipe. It's the linear combination. This much of cosine of t, this much of cosine 2t, et cetera, et cetera, et cetera. And then you can just summarize it into this. This, I put here, y divide the constant term by 2. You don't have to, and it's not at all a standard notation. It just fits in for us later. I'll show you later on. It's not important for now at all, really. But because a lot of them will just have a sub 0 or a naught. Excuse me. But the reason to do it is like if you want to condense it later on as we're going to, it helps with the indexing of like these, it fits in to this indexing a lot better, but don't worry about that for now at all. And then I had you, so what you're doing here is, if you look through the second page at all, right, you have to calculate all of these coefficients. So you have to calculate the a naught coefficient. That was one of the integrals. And I hope this made sense that I was having you look through, excuse me, I was having you look through the integrals here, like 5 to 7 leads you to this. So I'm just saying, like, if you take this and multiply cosine mt, which would just be a different integer value of than n here. So if you multiply both sides by cosine mt, you're able to simplify this down to a formula here. This z here, this is the set of integers. It only makes sense to do this on an integer value when you're looking at the periodicity of the functions. And similarly with sine, you get this as the formula. So basically these coefficients can be calculated. There's this formula for the initial term, constant term. There's this formula for all of the cosine coefficients, or scalars if you want. And then this term for all of the sine scalar, or this formula rather, for all of the sine scalars. So those all come directly, I just realized I'm blocking half the page with my face. Those all come directly from the integral sheets that you had been working on like Friday through the weekend, Monday, whenever. Okay. And so you can use those formulas if you understand the integral. That's why I said it's important to understand the integrals to see where those come from. But then you can just use them once you understand the formulas. They're very simple to look at. So this is a square wave function example here where the period's 2 pi. And I'm just saying that the function is defined as 0 between negative pi and 0, and then it's defined as 1. So it oscillates back and forth 0, 1, 0, 1, 0, 1. And the periodicity is described as every 2 pi it repeats. So just simply substituting the functions then into the integral formulas, this is the formula for the constant term. And so it's a piecewise function, so you have to add the pieces together. And you're taking the integral of 0 and the integral of 1, and it simplifies down, as you can see, to just 1/2. Now, that makes total sense because that constant term is like the sinusoidal axis of this. 1/2 is the value between 0 and 1 here. And that's what you're always going to be getting through that. Because think of how a periodic function works. Like if I go back to here, right, like and look at the full Fourier series formula, this is clearly, there's no cosine or sine associated with this. This is the vertical translation. This is the sinusoidal axis that's in it. So in our example, right, if it oscillates back and forth between 1 and 0, well, the sinusoidal axis is at 1/2. Okay, but that's proven through our integration here. All right, and then you'd have to go down and find the formula for the cosine coefficients. Okay, once again, it's a piecewise function, so you're taking, the formula says take the function times cosine nt, so it's 0 times cosine nt, integral 1 cosine nt, and this is nice because this just comes out to be 0. There is no cosine, there are no cosine terms associated with this. They both zero out. Obviously, this zeroes out, and through a little simple calculus, so does this. Okay, but with the sine terms, it doesn't. So when you go through and look at this is the formula for the sine terms here, and then you're taking both pieces, the integral from 0 to pi, negative pi to 0 with 0 times sine nt, and then 0 to pi of 1 times sine nt because it's a piecewise function. And of course, this zeroes out. But then when you integrate here, it does not zero out. These are always integers, remember, the values in there. And so cosine, it matters whether or not what the value is going to be if you're dealing with because it's an even function. So it matters if you're putting in a positive or a negative, right? Sine is, so in that respect. So basically all positive terms are going to come out, all even terms are going to come out to 1, and all odd terms are going to come out to -1. When you look at that, the cosine of 0 is 1, right? So if you describe that simply by putting in ones versus -1s, right? It's going to be, when it's even, it's going to be 1 minus 1, it's going to be 0. And when it's odd, you're going to have the -2 value in there, right? -1 minus 1 is -2, and then fixing that out here, -1 over n pi gives you this value here. And so these are the coefficients depending upon that. So when you put all of this together for a square wave function, okay, here is your constant term. Found that first. There are no cosine coefficients with this. So then, because of the fact that it's 0 when n is even, you only have to add on the odd terms here. So it's just when it's 1, it's 2 over pi. When it's 3, it's 2 over 3 pi. So basically, you can add that. You can just start to list out the infinite part of that. And if you want to summarize it, this would be a nice way to do it. So 1 over 1/2 plus 2 over pi. And then you could write out that it only matters when it's odd, right? And so define an odd number here. 2k minus 1 will always give you an odd number. So you can kind of just substitute that value in here. If n equals 2k minus 1, you could just start counting at 1, and it becomes 1 over 2k minus 1. Substitute the 2k minus 1 in here, and you've got a formula for this. I challenge you, if you want, if you have your calculators, start building this up in your graphing calculator, like 1/2, then add on the first term, then add on the second term, then add on the third term, and very quickly you'll see how this starts to converge to a square wave. It's kind of cool within just a few terms. Like it'll look like, if you don't have your calculator, I don't know if you do, if you left it at school or not, but like it'll have like a little wiggly part at the top, and then a wiggly part at the bottom, and then a wiggly part at the top. And every time you add on another of these terms, you add like another wiggle, for lack of a better term, wiggle, but you add on basically another cycle of the function in there. And so by the time you've got all the infinites, there's so many cycles happening at the top and so many cycles happening at the bottom that it looks like a flat line, like a square wave. Okay. So that's one example of how you can use that formula, those Fourier coefficients, to find a Fourier series. Okay. So I hope that helps. Let me know if you have any questions at all.